now. Okay, we have people coming, and I think we can start our webinar. So welcome everyone to Iclimabuilt, a webinar series. Today we will talk about the performance characterization of the building envelope, and today it's going to be part 1, which is about building performance simulation of advanced and smart materials. And yeah, and we are honored to have our the expertise from Iclimabuilt partners from Polytechnic of Turin and E2ARC as our invited speakers. And I will let them introduce themselves before the talk. And the first speaker is Fabio Favoino. And now the floor is yours.
Thank you, Nate. So I'm gonna share my screen. So you should be able to see my screen now in presentation mode, right?
Yep.
Okay, good afternoon, everyone. So today is the first of 2 seminars that we're going to do in the context of the Iclimabuilt project. So it's the first one, and we're going to talk about simulation, so building performance simulation of building envelope materials. And then the next one will be about testing and experimental characterization of building envelopes. So the contents of today, so it's going to be quite an extensive talk, so about an hour and a half. You can see the 6 speakers here. There is an added speaker with us as well, compared to what Nate showed. And that's myself. I'm associate professor in building physics at Politecnico di Torino, as well as Valerio Loverso in the same role. And then there is Ginevra Castri as PhD students in building physics in the same department. And we have 2 research assistants and assistant Andrea Gerbotto and Asir Rad, both in building physics in our department. Then there is also Angeliki Mavrigiannaki from E2ARC. That's an associate architect, project associate at E2ARC with us as well. And the talk is going to mainly done in 2 parts. The first, and after each part, we're going to have a short Q&A. So the first part is really about the methodology, the workflow, the tools that we're going to use, and the building archetypes that we're using. And then we're going to demonstrate the workflow with 2 applications, 2 case studies that are related to building envelope prototypes that were designed in the context of the Iclimabuilt European project. So a brief introduction, a bit the European project. So the objective of the Iclimabuilt project, Iclimabuilt, the full title is Functional and Advanced Insulating and Energy Harvesting Storage Material across climate adaptive building envelopes. And the main objective of the project is to provide a consortium that is supporting the scale up of building envelope technologies, mainly scale ups dedicated to SMEs, by providing one single entry point, so one consortium that is able to provide different testing, simulation, upscaling, and demonstration services. So you can see that it's a large consortium at the European level. We are 27 partners. Only 7 of them are universities, so there is a large contribution of RTOs that do applied research, and a lot of SMEs across 14 different countries. So the project in itself is divided into these supporting activities done within basically 5 main building blocks. One is about the production of specific materials, which are name called in the project pilot lines, and then by providing services in terms of material and building envelope component experimental characterization, and then building performance simulation, so a kind of virtual performance testing. But then on the other side, to provide an environment in which to validate and demonstrate these technologies into living laboratories, and then providing supports in terms of standards, testing protocol, and regulations. So today will be mainly talking about one part of these services, which is the violet one, so multi-scale building performance simulation. Within the projects, so we will use different terms. So when we talk about pilot lines, we intend the production facilities in order to deliver the materials that are then used in building envelope components, which also in the framework of the project, these are namely test cases that are then demonstrated into demo sites. And parallel to this, there is also an open call that's been currently just closed, in which we also provide support and funding to external SMEs to the project as a mean of external validation. So in the framework of this presentation, we'll mainly talk about materials and building envelope components, so pilot line and test cases. You can see that there are different test cases, each one representative of a specific part of the industry in terms of building envelopes, each of them with their specific features. And we're going to then look at two case studies selected among these 7 different building envelope components that are within the project that are most representative in a way. In the context of the project, the activity related to the performance characterization, either virtual performance characterization or experimental, is related to 2 main work packages, work package 4 and 5. Well, where work package 4 is related to the building performance simulation of innovative building envelope components in a, let's say, with a multi-scale and multi-domain approach. And then we will go a little bit in detail about that. So going from a material level simulation to building component to whole building level simulation, and where these 3 parts are all, 3 scales are eventually all integrated into one. The other work packages, work package 5, is the complementary of this, that is related to the testing and characterization of building performance of innovative building envelope components. So again, starting from material to laboratory characterization and characterization in real climate by means of outdoor test facility. And then there is a further scale, which is the living lab demonstration, which is not related to these 2 presentations. So we'll stop here at kind of full-scale mock-up characterization. So in general, in these 2 work packages, the word on which we are concentrating is building performance. So the first thing would be to define in a way what is building performance, and the related virtual testing activity let's say we do when we evaluate the performance of the building envelope. And to do that, I'll borrow a lot of build on the knowledge and the research that was largely carried out in the building physics group of Professor Jan Hansen at the TUI, where there is this formulated this definition in a way of performance, of building performance, that eventually is not represented by the cost of the asset, of the building assets, but rather of what the service that the building provides does. And eventually, performance needs to be something that needs to be measurable by means of a performance metric, a performance indicator. So to be measurable, need to have a clear definition, boundaries of measurements, and indicate eventually a progress towards a certain goal. When we look at the building envelope, though, in the early stage design, we always use eventually thermal solar properties and indicators of the performance of the facade, so to compare like for like different solutions that are, for example, thermal properties like Q value or eventually overall transfer of the building, the G value in Italy, the solar equivalent area, other optical properties of the transparent part of the building envelope, and so on. There are many to mention. Those are all have a physical meaning that makes sense for certain boundary conditions, which are steady states. And the purpose of this, using this, is that these are easily comparable. So like for like, so you can immediately compare a U value of a wall with a U value of another wall. And so these are non-context specific, okay? But they do not provide a direct measurements over a performance at the whole building level. And moreover, when we go from traditional standard building envelope to something that is can change its properties in its behavior according to the boundary condition, then this kind of metrics they do not make sense anymore. Just if we, for example, take the how you measure the U value, which is basically the slope of this line, and here we compare the U value of a double glazing unit with the U value of a double glazing unit that's containing a material that's changing the amounts of heat is transferred and absorbed, so phase change material. You can see that in a standard double glazing unit, yes, it makes sense. You can measure U value, while this kind of metrics lose sense completely when we use instead a material that doesn't have constant properties. In the same way, if we use ventilation within a cavity, you can see in the same way that the G value, which is in this graph, is the slope between in the slope of this line that inherently depends on the solar geometry, but when you use ventilation as well, that's a large change between the G value in summer or in winter conditions. So in a way, using these metrics, you cannot compare, and they lose the sense, or not providing a measure of the final performance. So for this kind of non-standard building envelope solution, but in general, to provide a measurement of the final building performance, instead, the metrics that we use that provide a measurement of the service of what the building does, that are much easier to calculate and to verify in the final part of the project, instead are metrics like total primary energy use, metrics related to occupant comfort, thermal, visual, aural comfort, indoor air quality, metrics related to view out, privacy, metrics related to operational cost, energy, or eventually carbon, whether that's operational carbon, embodied or life carbon. All these metrics, they don't have a direct physical meaning. Nevertheless, these consider the specific context, the dynamicity of boundary condition, the actual building that's on which you deploy the specific building envelope, so the effect of it on the actual building. Nevertheless, they are able to directly provide a measure towards the achievement of a certain performance. So the question is, okay, how we can bridge this gap between the final stage and the early design. And I mean, there are let's say the way this is usually done is using simulation, and in this case, simulation-based design, as a way to extend in a way the scientific method. So in a way to use a representation of reality, which is our virtual model, to test by means of simulation our design hypothesis and to observe what is the final performance on the building. And I mean, looking at that literature, it's well documented how these extended let's say, scientific method by means of using simulation can be applied to support the R&D activities, so to scale up the technology readiness level. And again, this is a graph taken from the work done by the group of Jan Hensen, but also adopted at the European level to show, let's say, the what's called the valley of death. So the difficulty that SMEs encounter in scaling up materials. And let's say this is exactly the target of the project, so of the Iclimabuilt project, so providing a consortium that's supporting SMEs in this TRL level. And how building performance can be used in different steps to support this activity, where the three key main part of this is to develop and adopt a modeling and simulation, a certain modeling and simulation strategy that represents the reality, to do this evaluation in terms of a comparison with performance benchmark, which is in our case the archetypes that we are using, and then to define the test case building models on which you're doing the simulation. So we will tailor the eventually simulation model according to the test case and the building envelope components that you're evaluating. So we'll look basically in the detail in these three parts. So this is done eventually normally in terms of energy simulation by always comparing the energy use, total energy use of the building you're designing, of the real building, with the energy use of eventually a reference building that's depending on the type of use of the building and the location that's used for performance comparison. So the energy label, at least in Italy, is given as a comparison with this virtual representation that has minimum requirements in terms of building envelope and building system parameters.
Yeah, you have to be in a hurry a bit.
Yeah, using building performance simulation in a way to support advanced building envelope components has inherent challenges. One are related to the multi-scale nature of this problem. So the influence of micro and nanoscale material parameters on engineering properties, the use of 3D printing and prefabrication, that implies also eventually complex geometry, but also requirements that are from the level of having different domains, so complex physical phenomena, influence between eventually thermal, daylight domains, acoustic domain, and so on. The fact that you're introducing maybe controllable properties and dynamic building envelope features, and then integration into the design process. This is more or less the framework of how this is achieved in work package 4. Of the objective of this part of the projects are dealt into this seminar are the last two. So defining the archetypes. So what are the reference models on which we apply the standardized BIM to building performance simulation workflow. So to be able to do multi-physics simulations. So basically the three contribution of the seminars that you will see is first part, the definition of the archetypes in terms of residential and office representative building, how we transfer them into a BIM model. And then a state of the art of what are the tools that can be used in a BIM to BPS simulation workflow, and the let's say the design, the definition of a unique workflow to use just one model for building performance simulation, and then the customization of this workflow in the two applications that will be showed at the ends. And I'll end to Angeliki. So Angeliki, if you want to share directly your screen.
Thank you, Fabio. Yes, I will share my screen now. I hope it should be in presentation mode now.
Yep.
Thank you. So good afternoon, everyone. My name is Angeliki Mavrigiannaki. I work for E2ARC, who is a partner in Iclimabuilt project, and we collaborate with POLITO in these activities that Fabio just explained. Our role is to define the building archetypes and create the archetype models in BIM environment to be then used for simulation. So in this session, we will cover the process of the definition of the building archetypes. We will start with the meaning of the term before moving forward to explain what is the purpose of the building archetypes, what are the criteria that guide their definition, and finally present the results of Iclimabuilt. So starting with the meaning of the term by strictly looking at the dictionary definition, it is defined an archetype as the most typical or perfect example of a particular kind of person or thing. Now, for research and scientific purposes, we focus on the words typical and example. In fact, the archetype approach is used as a scientific method for classification in various research fields. And in this context, an archetype represents the basic and recurring characteristics of a sample. So coming to discuss the building archetypes, these are defined as theoretical buildings that are representative of a group of buildings with similar characteristics. We come across representations of building archetypes in various settings, with the simplest example of the images that are shown in this slide, where we see some typical features of the buildings that convey information about the type and use of the buildings, and in some cases their structure, like in the first image, where we can this would be a common way to represent a wooden house. So in general, an archetype is the composition of the most common properties found in the investigated building group. However, it's not only the geometric characteristics that define a building archetype. And also, we need to have in mind that some archetypes are only representative of certain contexts, certain countries, for example. The wooden house that we discussed earlier would be an archetype in some areas, but not in other areas. So in order to generate the archetypes, first we need to define which is the investigated building group, considering aspects like the country of origin or climate that it is located in, the use and function of the buildings, and also the age or period that these buildings are coming from. Then in the next step, one would identify the most common properties of the buildings, which are both geometric and non-geometric properties. Another important question that comes up when we discuss the building archetypes is why do we need to define building archetypes and what are they used for? Commonly, the building archetypes are used for energy modeling and energy demand prediction at city, district, or country scale. And specifically for a Iclimabuilt project, we were interested in identifying a set of typical buildings that can be used for simulation of novel building envelope systems that are test cases. And the purpose is to benchmark the performance of the test cases against existing or common building envelope solutions, and eventually optimize the integration of the test cases in the building envelope. So in the next slides, we will see what is the process that was followed in Iclimabuilt for the definition of the building archetypes, and having always in mind the purpose that we have in Iclimabuilt. So first, in the first step, it was decided that our investigated building group represents both existing buildings that are candidates for retrofit interventions, as well as new buildings. The use of the buildings would be both residential as well as non-residential buildings with focus in offices. Then, for the country and climate that the buildings are located in, it was decided that this would be the 5 regions and countries that are represented in Iclimabuilt. Then, having completed the first step, we moved forward to collect the data for the most common properties per criterion of step 1. For example, the most common construction types and materials used per country and per building type. Our sources were first previous projects, specifically information gathered in the collaborative effort and results of Episcope and Tabula, which provided information about characteristics of the existing residential building stock. And then the projects Inspire and Hotmaps, where we could gather information for the characteristics of the existing office stock. The information about the office buildings is not so detailed as it exists for residential buildings. So we had to look for other information in published research, as well as in specific country reports, like in the case of Italy and Norway. And finally, we considered the country regulations for the non-geometric characteristics, specifically the U values for the new buildings. So having completed the 2 steps, we could move forward with the definition of and identification of our archetypes. And by considering only the use of the buildings and the country of origin, we could identify characteristics like form, area, and number of floors, which describe the geometry of the buildings. And this gives us the first abstract geometric representation of our archetypes, which would be similar across all countries for the same use. Then we need to consider that each of these buildings and each of these countries represent different climates with different heating and cooling needs. This graph presents the heating degree days and cooling degree days for each of the climates. So having that in mind, we understand that in each area, different materials are used and different compositions and layerings. So different construction types that result in differing U values of each component. Also different areas of windows, and finally different building services to cover the specific energy needs that are related to its climate. So these are all the non-geometric features of our archetypes. By combining the geometric and non-geometric features, we could eventually end up with our final completed archetypes. So we will see in the next slide that for residential buildings, we eventually concluded with 3 main archetypes for use and size of residencies, which are the single housing and the small and large multifamily houses. And then 3 main archetypes for the construction of the residential buildings, which are the heavyweight, mixed, and lightweight construction. And then for the non-residential buildings, we ended up with 2 main archetypes for use and size, that are the low-rise and medium-rise offices, and 2 main archetypes for construction, that are the heavyweight and mixed construction. Now, we had also to make some decisions regarding other aspects that would describe our archetypes. First, for the window-to-wall ratio, due to limited sources, we had to use background knowledge and, in some cases, regulation, and end up with some fixed values for some archetypes across all countries. For example, all single houses have the same window-to-wall ratio for the same period that they represent. Then for other geometric features like balconies, it was decided, in order to keep the whole process more feasible, to eliminate those from the description of the archetypes. So in this slide, we finally see the matrix of geometries of residential buildings. So as we said, the geometry is same for all countries, and differentiates only by use of building. And in some cases where there are very distinct characteristics, like the sloped roof, this was integrated in the geometric description of the archetype. In the same way, we moved with the matrix of geometries for the office buildings. Now, these matrices only and mainly give the abstract geometric representation, but do not convey the detailed information that is needed for the non-geometric characteristics, like the wall layers and materials that are used. So for this case, we had to move on with a more detailed documentation and recording. So for each specific archetype now that represents a country and a use of building and a specific period, we collected the information about the construction type and materials used, and recorded the sequence of layers as described in the sources, and then the respective layers that were used in our Revit model to create the model representation of the archetype. Having done all of this work, we could move forward with modeling our archetypes in the building information modeling software Revit. In Revit, we created the plan and layout of the building and its 3D geometry, and also inserted the materials that we discussed in the previous slide. Now, this model will be exported for simulation in Honeybee, as will be explained later by our partners in POLITO. And in order to ensure interoperability of the BIM model with Honeybee, a very detailed recording of the materials and their properties was done in an Excel spreadsheet. And this was not only done for the materials, but also for the rooms that represent the specific thermal zones that will be used for simulation, and information about the building program and program vintage, which are representations of the occupancy and settings of each room and thermal zone to be considered for simulation. A similar work and recording of properties was done for the windows, and for this case also we employed the application window developed from Berkeley Laboratory, which could give us specific information about the thermal properties of the frame. So after all of these steps, we now can move forward to see what are our final Revit models created for its archetype. In this slide, we see the updated